Okay, bringing in Mahima, Rafi, Karthika, and Aman. They'll be presenting 𝗀-𝗵𝗃, AI-powered semantic search for academia, a semantically aware search engine that uses fine-tuned 𝗀 for word embeddings and perform locally sensitive hashing to speed up the extraction of desired paper details with a given query. Over to you guys.
Thank you, Bhavana.
Thank you.
The ultimate search engine for an AI enthusiast would exactly understand what you mean and would give back exactly what you want. So that is our project, 𝗀-𝗵𝗃, a semantic search engine using locality sensitive hashing. Now we'll be seeing the problem definition. That is, we want to showcase the effectiveness of semantic search engine over the normal keyword-based search engine. So semantics means basically understanding the meaning of the word. For example, when we enter a query, father in a search engine, it fetches the results only containing the exact keyword father. But in the case of semantic search, it thinks like a real person. It fetches all the synonyms, that is father means dad, papa, or it fetches all the relevant results, even though if we don't include the initial keyword. So the main objective of our project is to assist the AI enthusiasts in getting all the relevant research works by understanding the user's in conceptual meaning and the context of the user's query. Now, the proposed solution. Our proposed solution is creating an academic domain-based vector search engine, which gives us an improved search result by understanding the concept and conceptual meaning and the context of the user's query to find the similar output. Now we'll be seeing how it can help. It is helpful for researchers who is working mainly in the AI domain, AI enthusiastic, to check the novelty of their ideas for the initial stage of idea formulation. Also, it is useful for AI-based literature surveys. Semantic search allows you to buy back your valuable time. Otherwise, that would be spent on reading a huge amount of research papers. The dataset that we have used are all neural IPS paper, which is a conference and workshop held every year, and we have used the archive dataset.
So the model we use is BERT-MAS language model, apart from BERT-NER or BERT classifier. The reason behind that is the MAS inputs are given and it has to predict the MAS inputs. So how is it helping us is it's understanding the context among the words and its multiple representations. And one of the advantages of using this model is it aids in next sentence prediction. So this can be useful in next text generation when the user is typing in the query. So for the fine-tuning purposes, we have used 𝗀 pre-trained weights. So 𝗀 is a scientific bird which is trained on huge corpus of scientific data. So we have to downstream this to AI-specific tasks to have fine-tuned based on our dataset. And then we have pre-processed on 𝗀 tokenizer. So this is the loss graph on fine-tuning. We could say that after certain epochs, it's overfitting. So to avoid that, we have taken previous checkpoints, like around 8 or 9, so that the model doesn't overfit or memorize.
Yeah, after converting all the headings like titles to embeddings, we will store these embeddings in a database. So, but our key constraint is we have to fetch the data within seconds or milliseconds to show to the users or our customers. So for that, to achieve that, what we had done is we had used an algorithm technique called locality sensitive hashing. So the intuition behind this locality sensitive hashing is, so we have a data and we have to group the data based on the similarity and store those groups in a backend or in a database. When we get a query from the users, we analyze the query and then we will find out which group it belongs to, and we will go to the database and we'll fetch that particular group, and within that group, we will find a more similar documents or research papers to showcase to our users based on the similarity.
Okay, now that we have seen things in parts, let's get it together. So we have used two data sets, and we have trained a model and validated using neural IPS, and we have generated embeddings for both the data sets. And these embeddings are the input for LSS model. We have trained on that. And the hash tables are stored in Google Bucket. So when the user types in the query, it's converted to an embedding, and the vector-based LSS search is performed, and top 5 out of 10 results are given out. So now, before going to demo, few things to see is, this is the graph which shows time taken on query search. So that is, before LSS, it was 12 seconds on query search, and after LSS, it's 1 second. That is significant considering 30K data points. There is an ambiguity in natural language. One is called polysemy, which says that a single word has two different meanings. That is, apple as an iPhone and apple as a fruit. And another thing is metaphor, wherein two different words have similar meanings and they're anonyms. That is ontology and knowledge representation in graph database. This is one thing to consider. And another thing is, we could say just include your NER model in query filtering. It eases the task, it increases the accuracy. Like example, pens by Pavlos, filter out pens and search for the pens and sorted by the author Pavlos. But there is a catch here. What if the input is Fisher GANs, which is a kind of a GAN, and we did not filter out Fisher from this? So this is one of the reasons we haven't used NER in query filtering. Now let's go to the demo.
Just a second. I guess you can see my screen.
Aman is not sharing. It says Aman Jolly has started screen sharing. There may be a button on the top which looks orange. You have to click the go button.
Oh, it's
it is okay. So this is the front end, and this is the live demo of the 𝗀-𝗻𝗃 app, the semantic search engine. So let's try a simple query, backpropagation. So as you can see, we are getting some relevant results, Laplace propagation, Brown propagation, and we have also added link to DOI so that user can scroll to that relevant research article. Also, let's try something else. Instead of backpropagation, let's try backtracking. So contextually, both are same in AI. So you can see, apart from this above dynamic backtracking, results are almost the same. It means our model is intelligent enough to figure out that backpropagation and backtracking are literally the same thing. Now, let's try some other things. Let's try ontology. So as you have seen in the example, ontology is equivalent to knowledge representation or graphical database. We are getting a paper title, knowledge representation. So this type of results is pretty much making sense. Now let's try some bigger sentences. If you can see this, I have this paper title, robust kernel bias aware prediction under covariant shift. So let's just try to see. So this is the exact paper title. And the best part is we have trained our data set on abstract, not on title, but still it is giving us the top results. Now let's just try to rephrase it. So we are using this paraphrasing tool called 𝗀𝗏𝗺. Just a second. Yeah. So it has paraphrased it. Let's just paraphrase it more. I will change shift to displacement, prediction to inference, and maybe robust to strong. Let's just try. okay, the results are changed, but still still we are getting some relevant result, the relevant title. So it is making sense, although the ranking has been decreased, but it is making sense. So our future work would be adding spelling rectification module and adding word suggestion module while typing of the query. And we want to make this approach memory optimized. Moreover, we would like to add document similarity module so that we can make semantic based plagiarism checker. That's all from my side. I hope you can see it. Yeah, thank you.
Are we done? All right, thank you very much. We have time for 1 or 2 questions. I see a lot of clapping. Ignacio is waving his physical hand. I guess he wants to ask a question, right? Ignacio, go ahead.
I'm an old school guy. A fantastic presentation, really interesting work. I see it works, so that's fantastic. Now, usually when I am looking for a paper or throwing ideas, I don't type a coherent phrase, but I throw in related words to my query. So my question is, in that setting, how does the model works? Can you get relevant results, or the model is having more problems?
Can you be specific on what kind of input you would be providing?
For example, I'm looking for, let's say, a model based on transformers that it's then using an RNN. So I will throw into the search bar RNN, BERT, machine learning, just to be sure. So can the model adapt?
Yes, we have tried these things on, especially when the prepositions goes in off, then I think the model is going nuts. It's it's not showing the accurate results, but when you give in the main words, like model transformer or something like that, it gives you the results, necessary results. But the moment certain things like I think or how is this, those kind of words go in, it's not gripping the good results for us. So we have to improvise that to acquire that generality of when the user talks in the normal way. How is it? How is that? What if? This is the thing we have to incorporate.
Good. And my last question is regarding future work. Are you planning on keep developing this? Because what would you do in order to improve the user experience? For example, some kind of ranking, sorting. How would you improve the transparency of your solution?
In the future, we would add in various sorting based on authors, titles, or any time zone like year. So we are thinking of adding those. And is anyone else want to add up to this?
Yeah, I mean, as far as this front end is considered, we can add certain filters. We actually need to add those filters so that search can be filtered as per year, search can be filtered as per titles, search can be filtered as per citations, number of citations. So yes, we are going to add that.
Fantastic.
All right, thanks everyone.